Based on observable and widely reported developments in the program, the second prototype of the J-36 represents a profound and comprehensive evolution from its predecessor, indicating a highly accelerated and data-driven development phase. The modifications observed are not superficial adjustments but are foundational revisions to the aircraft's core systems, reflecting a deliberate and strategic response to initial flight test data, computational models, and a refined understanding of the platform's intended operational envelope. The progression from the first to the second prototype suggests a shift from a basic proof-of-concept demonstrator, which validated the fundamental airworthiness and stability of the tailless, blended-wing body design, to a more mature and performance-oriented test article that begins to explore the full extent of the aircraft's potential capabilities. The most significant and telling areas of development are concentrated in three critical domains: the complete redesign of the air intake system for improved engine performance and stealth characteristics, the fundamental re-engineering of the engine exhaust nozzles to prioritize flight control and maneuverability, and the major structural overhaul of the main landing gear, which signals a reassessment of the aircraft's weight, ground handling, and internal architecture. The transformation of the air intake system is one of the most technically significant changes. The first prototype utilized a more conventional carrot-shaped intake, a design that relies on precise geometric angles to manage airflow but often requires additional components like boundary layer diverters to channel away the slow-moving air that clings to the fuselage. This slow air can cause engine compressor stalls and reduce efficiency if ingested. The second prototype has decisively moved to a diverterless supersonic inlet, or DSI, system. This system replaces the complex mechanical parts and the gap required for a boundary layer diverter with a single, precision-contoured bump, or bulge, located just forward of the inlet lip. This bump, combined with a subtly swept inlet cowl, performs the same function aerodynamically. It generates a pressure field that pushes the slow boundary layer airflow away from the intake, allowing only the fast, clean air to enter the engine. The benefits of this change are multifaceted. Firstly, it results in a substantial reduction in weight and parts count, enhancing reliability and simplifying manufacturing. Secondly, it improves the aircraft's stealth profile by eliminating the radar reflective cavity that a boundary layer diverter creates, presenting a smoother and more continuous surface to radar waves. Finally, it is engineered to provide stable and efficient airflow to the powerplant across a very wide speed range, from low-speed, high-angle of attack flight to high-speed supersonic dashes, ensuring consistent engine performance and reducing the risk of flameouts or instability, which is critical for the reliability and safety of the aircraft during demanding maneuvers. The radical alteration of the engine exhaust nozzles indicates a major strategic decision regarding the aircraft's balance between signature management and kinematic performance. The first prototype featured a deeply recessed nozzle design, where the engine exhaust was set well forward of the trailing edge of the airframe, creating a long, tunnel-like structure behind the engines. This configuration is predominantly focused on achieving a very low observable signature from the rear hemisphere, a critical aspect of stealth. The tunnel helps to mask the highly reflective turbine blades and internal structures of the engine from radar, and it also allows hot exhaust gases to mix with cooler ambient air and be shielded from direct view, thereby reducing the infrared signature. The second prototype has taken a markedly different approach, adopting a nozzle design that bears all the hallmarks of a two-dimensional, thrust vectoring system. These nozzles terminate much closer to the end of the airframe and feature a flat, rectangular, or slit-like appearance, as opposed to a circular one. This design allows for the exhaust plume to be deflected, or vectored, up and down, providing a powerful pitch control force directly from the engine's thrust. This capability is exceptionally valuable for an aircraft like the J-36, which lacks horizontal tail surfaces for conventional pitch control. The thrust vectoring compensates for this inherent design feature, granting the pilot superior control authority at high angles of attack, during slow-speed flight, and in post-stall maneuvers, where traditional aerodynamic control surfaces can become ineffective. The shift to this design strongly suggests that program engineers, after analyzing data from the first prototype, determined that enhancing the aircraft's agility, low-speed handling, and recovery capabilities was a paramount requirement, even if it involved a potential trade-off in the absolute minimalism of the rear aspect stealth characteristics achieved by the initial, more radical recessed design. The complete revision of the main landing gear from a tandem two-wheel arrangement to a side-by-side twin-wheel truck is a change that speaks to the aircraft's evolving structural requirements and operational parameters. A tandem gear, with two wheels in a line, is a mechanically simpler system but concentrates the aircraft's landing weight and ground loads along a narrower footprint. The shift to a side-by-side configuration, where two wheels are mounted on a common axle and often connected to a bogie beam that can pivot, represents a fundamental redesign of the aircraft's undercarriage and the internal structure that supports it. This new configuration spreads the aircraft's weight over a wider area, significantly reducing the pressure on the runway surface and improving stability during ground operations. This is particularly important for operations from potentially damaged or less prepared airfields. The change strongly implies an increase in the aircraft's maximum takeoff and landing weight. This increased weight could be attributable to several factors, including a larger internal fuel capacity for extended range, a more robust internal structure, more powerful engines, or an expanded and heavier avionics suite. The integration of this new gear necessitated a redesign of the wheel wells and their surrounding support structures within the wings or fuselage, which in turn can influence the overall layout of internal systems, such as fuel tanks and hydraulic lines. Furthermore, the geometry of the landing gear doors, which must seal perfectly to maintain the aircraft's stealthy radar profile when retracted, had to be entirely reconfigured to accommodate the different stowed position and shape of the new gear assembly. This single change, therefore, ripples through multiple aspects of the airframe's design, affecting its weight, internal volume, structural integrity, and low observable characteristics. In synthesis, the collective impact of these extensive modifications observed on the second J-36 prototype paints a clear picture of a development program that is both highly ambitious and exceptionally agile. The rapid iteration from the first to the second airframe, incorporating such deep and systemic changes, demonstrates a mature and efficient cycle of design, testing, analysis, and implementation. The aircraft is evolving from a demonstrator that proved a novel configuration could fly into a refined platform where complex trade-offs between stealth, maneuverability, weight, and structural efficiency are being actively explored and optimized. The presence of this significantly revised prototype confirms that the program has moved beyond basic flight sciences and is now deeply engaged in refining the performance characteristics that will define the aircraft's ultimate operational capabilities and tactical role. The continued flight testing of this prototype will generate invaluable data that will likely lead to further refinements, potentially visible in subsequent test articles, as the design converges toward a finalized production configuration.